So the last time we still had this theorem to prove when which said that the Turán density of these hypergraphs H T is the K factorial times the Lagrangian of cliques which we also had determined before as this. Right, and so to determine this, we had used this nice little observation that when we have an automorphism between two vertices, then we must have a maximizer of this polynomial in the definition of Lagrangian that has the same value for those two vertices, which we call equivalent. And since in the clique any two vertices are equivalent, we have that that we need to have a maximizer which takes the same value for all of the vertices. So this thing here is this P K T K of 1 over T. Okay, and then that gives this. Okay, so let's prove that. To prove anything, well, prove Turán densities with Lagrangians, the only tool that we looked at is this proposition. So, which told us that the Turán density of F is the supremum taken over all K factorial H over all F Humphrey and dense H. So H F Humphrey dense. And so dense, we also had the observation for that we know that a hypergraph can only be dense if any two of its vertices are contained in an edge together. And so now we have that. So since K is H T plus 1 K this from 3. So are all the blowups of that. Okay, and so those are all potential candidates, right? Because these are clearly also dense. But on the other hand, we want to say that we are not. So maybe. So why are these? So recall that this one was defined by taking T plus 1 vertices, and then for any pair of vertices, we add an additional outside vertices and connect them with that pair. Okay, so as an example for T equals 4, we would take this, and then so T equals 4 and K equals 3. We would take one more vertex for each of the pairs. So these are the ones for the inner pairs that I didn't want to draw. This, and then one of these vertices goes with one diagonal and the other one.
So will you please remind the definition of HT plus 1K?
Yeah, that's what I'm just saying. Right, so we have our T+1 vertices, and then for every pair, we have additional, for every pair among these initial T+1 vertices, we have k minus 2 other vertices, and those vertices together with their pair form an edge. Okay, so why don't we have a homomorphism from this? So any such homomorphism phi would map two of these x vertices, which were the inner ones, so xi, xj, to the same vertex. To the same partition class. But then phi xi and phi xj are not in an edge. Of so therefore, these cakes of size t are some of the candidates that we consider in this supremum. And on the other hand, I want to say that any dense hypergraph on at least T+1 vertices is not free, so not F hom free, this being the F. So why do we have this? Again, right, we have our x vertices and x1 to xt, and then these y ij1 to y ij k minus 2 for every pair ij, and then these two together with the respective two x vertices form an edge. So we can just, when we're dense, we know that any two vertices are contained in an edge together. So we just embed these, which are for us now T+1, right? This is the definition of each key. We can just embed these arbitrarily. And then since we know that in a dense H, any two are in an edge together, so we just find some k minus 2 set, which together with these two vertices forms an edge. And we don't care whether maybe we will map many of these vertices to the same y's or to even to some of the x's, because we know that that we just want to check that we are hom free, right? And that would still be a homomorphism. So embed the x1 to xt+1 to arbitrarily to distinct vertices. Then any two of these, or anything. Say A1 to AP plus 1. And then since H is H is dense, any two of these by some so for I j, any ij, let's just map our yij's to some such k minus 2 set, which forms an edge with the respective ai and aj. That forms an edge with a and then this gives the homomorphism. So that means that in this supremum above, we can actually just restrict ourselves to H, which have at most T vertices. And then again, since we're always monotone, right? This Lagrangian is always monotone because in a clique, we can get any other subgraph by, or we can be at least as large as the Lagrangian of any subgraph by potentially placing some of them as 0. So here to the maximum A factorial H most T vertices dense. And this is then the K factorial times Lagrangian of the clique on T vertices. And that is so now we move on to the next topic, which is the codegree Turán density. Okay, so this is a variant of the hypergraph Turán density. And as I said in the very first lecture, basically we should just think of the Turán density as one very natural instance of how we can think of problems in extremal combinatorics. We want to ask for the threshold in one of the parameters of our structure. so in that case, it was the edge density, above which we are guaranteed some property, which in our case was just containing a certain subgraph. And here we also want to ask for the threshold above which we contain a certain subgraph, but that threshold should be in the minimum codegree. So first, let's say what the codegree is. So generally for a K-graph H, so H and some vertex subset, the degree of the vertex subset of S is ds. It's the number of edges which contain n. Maybe such that. Okay, so in particular, if S is just a singleton, then this is just the degree of the vertex. But for three graphs, we can also ask for what's the pair degree, right? We looked at that before in some of our Turán problems. So we take a pair XY and we ask in how many edges is this pair XY contained? And generally, we can ask this for any S. And we then also can define the minimum degree of H with respect to sets of specific size. So for I in K minus 1, the minimum I degrees H is delta I H, which is just the minimum taken over all sets of vertices of size I, and then taking the degree of S. Okay, and so these kind of conditions are also studied a lot for Hamiltonian cycles, right? So one of the three examples that I had in the beginning was Dirac's theorem for graphs. And by now we have some generalizations of that to hypergraphs. And this is the kind of minimum degree condition that is assumed. Okay. So the codegree is now just this for K minus 1. So the delta K minus 1 H is also using the codegree. And now we can define again the extremal number, but now the extremal codegree number as the maximum minimum codegree such that we still have an F-free graph with that minimum codegree. So or K graph and of and F is maximum delta K minus 1 H for a F free graph. Okay, so if we have a minimum codegree larger than this, then we know that we must on n vertices, we know that we must contain vector. And now one can also look at the limit. However, here the argument is a little bit, it's not very complicated, but here one actually has to prove the existence, which we will not do here, but that's why we call this definition plus lemma, and this is due to Mubali and Zhao. We introduced this this concept, and so the codegree Turán density of the Q-graph F is the limit and to infinity the extremal codegree invariable. And then we divide by n. Okay, so maybe you would expect that here we should divide by n minus k minus 1 or something, but in the limit that is the same. So we just divide by n. And yeah, so and this is and it's also lemma because we need the existence of this limit. Okay. Now we can ask what is the codegree Turán density of some hypergraphs, and maybe let's also remark that we again have supersaturation and the corollary. So in particular, we know that the codegree Turán density of F and the codegree Turán density of any blowup of F are the same. Okay. So in particular, when we are in epsilon above the codegree Turán density and we have many vertices, we know that we have many copies. So some constant c times the order of magnitude of what we want. Okay, and so now let's see how one can determine this, and we will pursue this way with a theorem by Mubali, which says that the codegree Turán density of the Fano plane is 1/2. Okay.
For the supersaturation, you will need this hypergeometric distribution thing.
Yeah.
Instead of just counting for the density one, right?
Yeah. So I mean, so basically, for the supersaturation, we want to say that we have many subsets which still have, with respect to their number of vertices, still have roughly that minimum degree condition within that subset. Okay, and that is also basically what is used to prove that the limit exists. Okay, so for the lower bound, we just remember the extremal example that we had here for the Turán density. which was do we remember which one it was? This bipartite balance bipartite. Okay. So of course the minimum codegree of this one is not necessarily what the density was. So here for this pair, the degree would just be this side, so it's roughly n half, right? Okay. So for the upper bound, need to work a bit harder. And interestingly, we first want to prove a Turán type result for the following family. So that F2 being the three graph and by taking a K4 minus and blowing up the apex. So the apex in the K4 minus is the unique vertex that lies in all three edges. So in other words, we look like this of 5 vertices, and we have all edges of this type. Okay, so then this vertex sees a triangle in the link here, which is exactly a K4 minus, and this vertex also sees a triangle in the
So blowing up it into two words.
sorry.
You didn't say blowing up into how many verses?
Oh, yes. And so then we iteratively define a family Ft. P larger 2 define the family of three graphs. As follows. So Ft. We take an element of Ft minus 1. We add two vertices, and then any t edges from these two vertices to the vertices of the previous member. So consider all three graphs obtained by taking f in Ft minus 1, adding vertices x and y, and and T edges of the form A x y with A and the vertices of that previous one that you do. So we can think of it as we have here our F in the previous family. And then we take X and Y. And T vertices here. Okay. And now we want to use this lemma, which is between Bjarne and Schülke, which tells us some properties of this family. And the properties are one, just the number of vertices. That's 2t, it's 1 vertices. So that of course just follows by induction, but we just want to be able to refer to it. 2 is any t set, any set of at least t plus 2 vertices in a member of Ft induces an edge. So any t plus 2 F in Ft induce an edge. And the third thing is that we have an upper bound on the Turán density of this family. And we'll also look at the proof of this in a moment, but let us first see how we can use this. So maybe you take, so given epsilon, take some t that's large compared to epsilon, and then some large n0, and let h be big graph on n vertices with minimum codegree, which is now just a 2 degree. One half plus epsilon n. Okay, and then we need to show that this H contains a copy of the Fano plane. Okay, so first, this thing always translates to the same constant as density. Okay, so note that the number of edges in each is at least, so we can count from each pair, we sum over all pairs, and we sum the number of edges that this pair is contained in. In that way, we count the number of edges 3 times, right? Each edge is counted from the perspective of each pair. So we get 1/3 times n choose 2 times 1/2 plus epsilon n. Okay, but this is greatly equal to 1/2 plus epsilon n choose. Okay, so we have this codegree, then we have this density. And so now we know that H contains a copy of one element of Ft by our third property. But again, by supersaturation, which also holds for families in the same way, we know that actually we find a 2 blow up of some member of this family. And let's call this one maybe F. Or it's F2, which we then call F prime, for some F in our family Ft. This is by property 3 in the length. It is our Turán density of these small. So then for every x in the vertex set, okay. So then x and x prime be the vertex set of this copy of F2, such that we have one of the copies of F, so not F prime, but F on X, and one copy in X prime. Okay, so in other words, we want to, for this 2 blow up that we have, for every vertex, we now have 2 copies, and we want to put one of the copies into X and one of the copies into X prime. And then let X prime be the copy of some vertex X in the first set X. Okay, so you just want to have this short notation. So now, what will we do? Let's say here we have X. And here we have X prime. We will look at the co-neighborhoods of a vertex X and its and its copy x prime. And we'll sum over all of those. And so each of those co-neighborhoods is relatively large. I mean, for instance, they have to overlap, right? Because we have more than half, but that's not the point of the picture. So the point is that we will find one vertex that lies in many of the co-neighborhoods by double counting. Okay, but if it lies in many of them, then we will have so many meaning t plus 2, then those t plus 2 vertices will induce an edge. But so an edge here is, of course, not only this edge, but we have the same edge over here in the copies. And not only that edge, but also all the edges where we exchange one of these vertices by one of these vertices, because our f prime was the blow up, right? So each this vertex can play the role of this one in each of the edges, and similarly for these. So that will put us in a position to find the funnel plane. So for it's fine. The neighborhood of x and x prime be the co-neighborhood. So this is all the y in b of h such that x prime y is in h. Then summing over all x and x, the sizes of these. Okay, so this co-neighborhood by the codegree condition, we know that this is at least 1/2 plus epsilon n. And we sum over everything in x. So we can use that we denoted the number of vertices there as 2t plus 1. Which is, so here we essentially have t, but then because our t is much larger than epsilon, so we certainly also get still something when we multiply this 2t times epsilon. So this is greater or equal to t plus 2. T plus 2 times n. Means there is a vertex 1, which is contained in the co-neighborhood of x and its copy for at least t plus 2 x.
Okay, t plus 3. Yeah.
Yeah, we can have even more, but we just need the t plus 2 so that we get an induced edge. So this set this set of vertices by lemma, the second one, induces an edge. Say ABC. Then we claim that the set of vertices A, B, C, A prime, B prime, C prime, and Y induce. Okay, so let's check that. We will draw the Thunner plane like this, and I want to. I mean, it doesn't really matter, but let's just put this ABC here. We know that we have this edge because that was exactly this edge that was induced. Then let's place Y here. And let's place for each of these its copy opposite with respect to the Y. So this is B prime, this is A prime, this is C prime. Then by the choice of Y, right? Y was this vertex that was contained in the co-neighborhood of a vertex and its copy, and these ABC were chosen among those vertices which have this property for Y. So in particular, we know that we have this edge, and this edge. And now for the remaining ones, okay, so let's check this circle in the middle. We have B, A prime, C prime. But that's the why I stressed up here that we have many more edges, because we also have, we don't care essentially about whether it's the prime version or not the prime, because they are just copies of each other. So we know that we have this edge. Then this one is just ABC. And this one is also ABC. Okay. Any questions until here? Otherwise, I would move on to proof the lemma. So the first part is just induction on the number of vertices. On T. And I mean, all of them are induction on T, but not all are vertices. So the second part, again, we do induction on T. And for the base case, you can just check it. So let's just do the step. So if we have T plus 2 vertices, let's think of it again as we have our copy F in Ft minus 1 and our 2 additional vertices X, Y, which see these. We will say that, okay, either we have at least T plus 1 vertices in here, which is T minus 1 plus 2. So we have it by induction, or we need to have these 2 vertices. But if we have these 2 vertices, then if we so they have T neighbors to here, but how large is this set of vertices? It's just 2T minus 1. So we cannot have that we pick T vertices from here, and none of them sees an edge from these. So let F in F prime and F T such that it is obtained from some f in t minus 1 having xy and t edges a xy, right, as in the definition. Now let S be some subset of f prime of size t plus 1. The t plus 3. Then if S intersects the vertex set of F, which was in our, remember, in F t minus 1, if this intersection is of size at least t plus 1, then by induction S induces an edge, which is an edge in F, but F is a subgraph of F prime. So if not, S must contain both x and y, and t vertices in V of F. Since x, y, see t edges to that vertex set, meaning their t vertices such that x, y together with that vertex form an edge. But the number of vertices in VF is only 2t minus 1. There must be some a in VF such that a x1 is an edge in F. Okay, so this gives us the second part, and now the most interesting part is part 3. So again, we do induction on T. And yeah, so let's here maybe say what we do in the base case. So recall that the Turán density of the K4 minus, we proved that it's less than 1/3. And smaller equal to 1/3. And so for some constant C, and so C doesn't even have to be very large. No, so C maybe we could reasonably large. We have that the extremal number of the K43 might let's say of FT. So F2 is just the family consisting of that one graph that I mentioned in the beginning. That this is at most 1/2 n choose 2 plus C 2C times n squared. Okay. So know that the Turán density of our F2, because it's equal to the Turán density of the K4 minus, is smaller equal to 1/3. But here we want the supersaturation, and then we want that really the extremal number already at that n is below that value. So that's why we choose this C. It's basically a different way of saying that we want this for n large enough. But because later we will do an induction also on n, so we don't want to say n is large enough. So we just put a constant. So t minus 1 to t. We do an induction on n. And so if n is equal to, or so, and what do we prove by induction? N.
Something strange here. Why it's a quadratic thing? For extremal number, if you really mean extremal number, it shouldn't be cubic.
So this thing here is cubic, yeah. But this we want squared, right? It's sort of, it's a lower order term, but that's exactly how it helps us deal with the small. No, sorry, this definitely is quadratic. And so by induction on T, we actually want to show, so that this form holds generally with the 2 replaced by T. This T is more equal to 1/2 and just 3 plus 2 plus T C n squared for all n. Okay. So that's why now when we go from T minus 1 to T, we want to do an induction on n. For n equals 2t plus 1, this holds by, or trivially, because so our C, right, that's why before I said that it should be maybe greater than 2. If n is 2t, then this later part is essentially, because our constant is even larger maybe than 2, then this would essentially be t cubed divided by 2. And so if this constant is large enough, we're larger than this. Because again, here we would just have 2t essentially. So for the inductive step, in our inductive step, let H be a big graph on vertices with more edges than that. Or Okay. And what we want to do here is similar to what we saw in the second lecture. We want to look at several links of different vertices in a weighted way. And we want to say that on the one hand, because of our degree condition, these weights must all be quite large. But if they are large, then we will find an FT. So at which links do we want to look? We know that for FT minus 1, we're already below the extremal number. So we find a copy of some member of FT minus 1. So by induction on T, we know that F is an H with some F in family FT minus 1. And let now L be the multigraph on the vertex set minus the vertices in F. With an edge every edge in the link one of the vertices of this copy of F. Okay, so now if any pair would have multiplicity T, then that pair together with a copy of F would give a copy of our or one member of our family FT, right? Because if here we have our copy F, and now we are told that the multiplicity of this pair is at least T. That means that we can find some T vertices here, such that we have all these edges. But that's how we defined a member of our family FT, right? FT is the family of all three graphs that can be obtained in such a way. So okay. So we know that every pair has multiplicity below that, so at most T minus 1. And then by averaging, there's a vertex in the F. Let's say vertex V in the F, which has relatively small degree. So why is that? So by averaging Now, because these multiplicities just meant the link edges. So if each pair has multiplicity at most t minus 1, then we average over our vertices in F, which would 2t minus 1. And then here we have the number of pairs in the complement of F. So n minus 2t plus 1, choose 2. And then we also need to count the pairs that the edges that maybe take 2 vertices in F, so V and some other vertex in F, and then a vertex outside. But how many do we have of those? 2t minus 2, right? The other vertices in F times the vertices in the complement. And lastly, we should also count just the edges which our V has within that F. Okay, so 2t minus 2, choose 2. And oh, this should be 2t minus 1. Minus, oh yeah, minus 2. Okay, so now this thing here is smaller than t minus 1, 2t minus 1, and choose 2 plus 2 t n. And but that means that we can delete that vertex and then apply induction. Right, so just for maybe mental orientation, currently we are just proving a lemma. So we're talking about a Turán result, so we don't need to say that if we would delete this vertex that we preserve some sort of codegree. Okay, so now deleting V gives the key graph H prime on n minus 1 vertices with the number of edges would be even straight. This minus this number and okay, but this thing here was at least 1/2, yeah, 1/2, and choose 3 plus TC n squared. And then here we get that this is greater or equal. Oh, yeah, here we have. I mean, it doesn't really. Get that this is greater or equal then minus 1 choose 3 plus E C n minus 1 squared. Okay, and so by induction, H prime is okay. Any questions about this main proof? If not, then we move on to the following. So the type cycle, so type a uniform on cycle is a K-graph with vertex set let's say x1 xl and edges xi to xi plus k minus 1, where we view the indices modulo L. And the length, yeah, it's just the number of its vertices and the number of the edges. And so this is also what's, as I mentioned, the Dirac results for hypergraphs. This also usually the definition of a cycle, and then would be Hamiltonian if every vertex was contained in the cycle. And so maybe as a remark, Caltech, let's and Pokrovsky determined the determinacy of long free uniform cycles. So also one thing one can see very easily is that if the length of the cycle is a multiple of 3, then you can just get it by blowing up the single edge. Okay, so I mean they didn't just do that; they determined it also for the well, I mean like the thing for divisible by 3 wasn't of course known before, but they determined now the other lengths for long enough. And Bannock and Luo determined the determinacy of long C B L minus where this minus just means that we delete one edge from the set. So and so a short result that I can show now is a codegree version of this. So this is due to Giga. So this itself, where we showed that the codegree, so for L is 5, we have that the codegree Turán density of the uniform type cycles minus an edge is 0. So again, of course, for the length divisible by 3, this is just a subset of the other cycle, which we can get by blowing up an edge. So for that, it's not interesting. But and so actually, the only really interesting case is L equals 5, because after that it follows from blowing up. So it is easy to change. And once we know this is 0, then result okay, so what is the idea here? Maybe let's first look at what that tree graph that we're interested in looks like. Okay, so we have all edges when cyclically going around, apart from this one in the top. But this, we can also say that this vertex we call X and this one Y. We can also say that this is the same as when we look at the link of X. So we see a path with this vertex being Y, and this in the end we call them AB, and in Y we also want to see this edge AB. Okay, so this edge AB, so here we have X, and in the link it sees this 3 path, so with Y on one end and then AB on the other end. And so this covers, right, you have 4 edges in total, and this covers 3 of them, everything apart from Y, AB. But this last edge is now covered by this second. So this reduces the problem to finding 2 vertices which relate to each other in this way with the links. And how do we do that? We will define nice pictures as, so for vertex X, a nice picture consists of some set here that's reasonably large, which will be called S. Then a vertex B here, and then a collection of pairs here. such that for every vertex in here and each of the pairs here, so these are ordered pairs, which again doesn't really matter, but this is how one can write it down neatly. So for every vertex here, and then the first vertex of that ordered pair here, we want to see the three path. So this and then this should be an edge, such that this forms a path of length 3. And we also want that this thing here is also reasonably large. So this should be roughly, let's say, epsilon squared n squared or something. So if we can find these in a nested way, so find a nested sequence. With Si containing Si plus 1 and X I being in Si minus 1. Yeah, okay. Then what we will end up with is we have some Xi here with its Si Bi, which is a neighbor to everything here. And then this collection we call Pi, such that we have all these three paths. Then somewhere below, we must have some xj for which this set intersect this set. Because if our sequence is longer than roughly 1 over epsilon squared, then these sets at some point must overlap. But now this xj, because these are nested, and we always recruit this one out of the previous si, or sj minus 1, we know that this guy is also contained somewhere in here. Okay, so this one is that vertex. And now we don't even care. Of course, here we also have this nice picture. But we don't even care for any of this part. The only thing that we care about is that our overlap. So we have one pair here, which also appears here. And then we exactly have found these two links, right? We have the first vertex, which sees a three path in its link, this three path, such that the first vertex sees itself in its link, the last pair, which is this yellow thing. Okay.
So there's no Bi, right? Just a single B. Only Si and Pi are.
Yeah, this is a single B.
Bi and Bj could be.
They could be different. We just want to
Right. Okay, that has nothing to do with that B. Okay, right.
Oh, yeah.
Okay, yeah.
So let epsilon given and be much larger than this one, and then H be a sigma on n vertices with minimum 2 degree at least epsilon n. A nice picture. Exists of a vertex x the set S of vertices, another vertex B, and the collection P of pairs. But we want to take out S, just so that we don't have interference by potentially using some vertex from the front. It doesn't really matter because anyway, everything is so robust with the epsilon and the order of magnitude, but yeah, it doesn't really matter. But anyway, let's right. So this, and then here we take ordered pairs, such that for every S in S and XY in E, S, B, X, Y forms a path of E in the link of B. Okay. So we want to find an acid sequence. So some ST sense with T, we want to choose as 5 over epsilon squared plus 1. So this is the thing so that we can get the pigeonhole here. And each of these sets should also be still reasonably large. And nice pictures. VI, SI, BI, PI. But those just, so this S0 is some sort of initial set that doesn't appear in these pictures. So the I is just starts with 1. Such that the this PI is also relatively large. And like that, we just this with 5. Okay, so if we find this, we are done by pigeonhole. Because of this and the choice of our T, we will get that because they're at most n squared ordered pairs. So after T steps, we need to have some, the 2 of these sets of ordered pairs need to have an overlap. And then we are exactly in this situation. So yeah, maybe let me just sketch how we can construct this picture. So assume that we have constructed the previous pictures. So 2 rows. So let's say that we have constructed our previous picture with vi, some si here, vi, and pi. And now we want to construct the next picture. Okay, so we just can recruit vi plus 1 out of this vertex set. Okay, that's not a problem. Then the crucial thing here is that these pictures are easy to construct if we just know that we have in a graph a minimum degree condition of epsilon n. But that's what we know, right? Because of our minimum codegree condition, we have that this as a graph has minimum degree at least epsilon n. Because this vertex together with each vertex in here forms a pair. That pair must be contained by the minimum codegree condition in at least epsilon n edges. And therefore, in the link of that vertex, each of the vertices here has degree at least epsilon n. And so we take our previous set Si minus maybe this vertex that we took out. And we double count the edges that leave this set. Okay, so since each vertex in here has this degree, we know that it's the size of that set times this. But then by double counting, what we actually also counted is the sum of all the neighborhoods of vertices outside inside this set. And that tells us that there must be a vertex here whose neighborhood in here is of size at least epsilon half times the previous set size. And then by induction, that gives us this set size. Okay, but then from here, we can just walk greedily, right? We say to get these pairs, we say, okay, how many choices do we have for this one? Essentially, epsilon n, we have to be a bit careful because we want to take out this set. So maybe we have epsilon half n. And then maybe for the second one, we need to be even more careful because we also want to exclude this one. But okay, it's maybe epsilon half minus 1. And that's what gives us this epsilon squared over 5 times n squared. Okay. And yeah, so this this method of nice pictures can also be used for different grid graphs to show that they have codegree Turán density 0. And yeah, it can be generalized. Stop. Any questions?